Good morning, everybody. My name is John Nichols. I'm president of the Tutors Association. I have been for a few years. And today I'm going to be delivering the first part of the educational theory mini-series for the TTA summer sessions, which is very exciting. So pleased to see so many of you have managed to arrive this morning who want to learn a bit more about educational theory or just discuss it in general. Today's session is going to be on schema theory. So if you can all see my screen and it's changing for you, then that's great. So we're going to talk about schema theory and in particular what it is, perhaps what it's not. And the first thing to bear in mind is that schema theory is a theory. Doesn't mean it's not good or not useful, but I don't want any of this you to come back to this in a couple of years' time and say, well, John said this, why is it not true anymore? It might be the case that things change over time because this is something which is we acknowledge this is relatively close to the edge of what we currently know in cognitive science and neuroscience. So this is a best current model that we have. There's likely to be refinements in future, and I don't want you to think that this is biblical truth or something. But we are going to try and go through the four key main areas of schema theory, which will hopefully directly relate to teaching and tuition practice. So you can be able to draw some conclusion as to, okay, well, this is what schema theory is. What does it mean in a teaching context? It's not supposed to be completely abstract and separate from the day-to-day teaching that you will probably all do. It is supposed to relate directly to the tuition practice that you will all have and deliver it day to day. So there are four main principles we're going to cover today. It's by no means completely exhaustive, but it should give you a good overview. So the first is about information being stored or probably being stored as schema or schemata, and a bit about what they are. The second part that we're going to go through then today is about how that relates to learning things and why pre-existing knowledge is particularly important. You've probably already aware that it's easier for children to learn things, or easier for anyone to learn things, if they already know something about it. And this will help to explain a bit about why that's particularly important and how. The third part of what we're going to cover today is about rehearsal and retention and the strength of connections. I'm pretty sure you all have heard the phrase practice makes perfect. I'm sure you've told your students many times to go away and practice something. This gives us a bit of the understanding behind why that works and also how we can try and make it more effective or things that might make it less effective. And then lastly, we're going to try and talk about motivation. Motivation is a particularly interesting area. We all want our students to be more motivated, and this will help to address some of the potential ways in which we might be able to do that. So we've got an action-packed hour for educational theory enthusiasts, which I hope you all are, or at least will be by the end. So we'll get started. If at any point you've got questions, feel free to use the hand option throughout. What I'll probably do is address any questions that come up at the end of each slide. So if you have questions at any point, feel free to use the little hand at the bottom of your screen, and then we'll address any questions at the end of each slide. There is space at the end of the session for questions on the whole topic, so you don't have to ask them on the way through. You can save them for the end if you wish. Right. So without much further ado, what is schema and what is the whole basis of schema theory? So we'll show you a diagram to try and make it a bit more clear. So a schema is a rich, dense network of related information. So if you imagine any particular concept, in this case, a house, okay, anything that relates to a house or that is connected to a house is part of the schema that we would describe of a house. So there is a lot of different things that you'll be aware of. It has walls, it has windows. You know what the walls are probably going to be made of brick. There are rooms, bedrooms, bathrooms, kitchens, living room, whatever. All of these things you're aware of. They're your surrounding contextual knowledge of what a house is. If you try to imagine eliminating all of these other memories around it. So if you didn't know anything about what houses are made of, you don't know what they look like, you don't know what houses have got or what they're used for, then I want you to try and think about, well, what actually do you know about a house? I mean, okay, you know the name, but these are all things that relate directly to the meaning of the word and the concept. So the idea in schema theory is that the understanding any particular concept requires us to have this connected information that relates to other facts or other things that relate to the central concept, which in this case is a house. Okay. Now, you can have a well-developed schema and you know a lot about something. So for a house, you're all going to know quite a lot because you all live in one, I presume. And there are some concepts where you'll know next to nothing or nothing at all. I mean, unless you're a history teacher, you might not know a lot about Alexander the Great. So you might just know he's Greek or Macedonian, but you might not have very much of a schema. You've heard of him and you not much else. If I give you some other particular figure, for example, if I told you my mother's name, probably none of you have ever heard of her, and that's totally fine. She's not famous, so it's not expected that you're going to know who she is. But your schema in that sense is nothing. You'd hear the name, and you might recognize the name as a name that's not that uncommon. But then you would know nothing else. There's no other surrounding knowledge. There's no network of related information for you, apart from the sound of the name and the fact that it is a name. Yeah. If I give you a name of a person in a different country, which is completely different and doesn't sound like any names you've ever heard before, your schema is even less. You know nothing at all. You don't even know if it's a name. If I say Toyotomi Hideyoshi and someone turns around and actually knows what I'm talking about, then good for you. But I mean, most of you probably will sit there go, have no idea what or who that is. So a schema is a rich, dense network of related information that we can use to understand what a particular idea is. So first off, why do we think this is the case? Well, we don't store information in our brains like computers do, or like a library. Sometimes people have used a library as a metaphor for human memory, and it's not really very useful because we don't file things away in sort of discrete books that are unconnected to each other. There's no real way in which we can imagine the brain as we understand it, made of lots of nerve cells with lots and lots of little branches. There's no way we understand that they act as a library where you sort of access a book, open it up, read it. That doesn't seem to work in our brain in any way. There's nothing in our brain that does anything that looks like that. And I don't know if any of you know anything about computing. Maybe you don't. Excuse me. But computers store information in a very different way as well. They store information either via transistors, so electronics. They store the sort of tiny buildups of charge, or the way that transistors and capacitors are arranged within computer memory. It's not similar to the way we store information in our brain. In those situations, there is literally a finite bank of places where you can store either a 0 or a 1, or a positive or a negative charge. But they don't work in the same way that the brain works. They don't have interconnections in the same way. Obviously, there are connections in computers, but they don't have connections in the same way. So we don't work the same as things that we know of that store information. So what do we do rather than what we don't do? What we do is we then build the connections between networks of neurons that represent ideas. This is the second bullet point. Okay. So you will understand really, really basic things, like you'll be able to recognize if I give you a horizontal line, a pen like this, or a vertical line. And it's quite easy for you to notice if I'm showing you a horizontal pen or a vertical pen. Now, for very, very simple things like that, which are effectively just visual information, they are stored by very, very simple networks. And in some cases, we've actually been able to track individual neurons, which someone did a study years ago, over 15 years ago, 20 years ago, on cat brains, very similar to human brains in many, many ways. And cats have a neuron, which they found, which literally fires only when they're looking at something which is horizontal, and it doesn't fire if they look at something vertical. And the closer something gets to horizontal, the more it fires. So if you look at something like this, or if a cat looks at something like this, it should be specific, then that neuron was firing loads. And the more you tilt the pen, the less that neuron would fire. And when the pen or when any line was shown to them that was vertical, that neuron really didn't fire at all. So for very, very, very simple ideas like geometric shapes or simple lines or light and dark, they can be encoded by individual neurons or extraordinarily simple networks. But for anything that's more complicated than that, obviously we need to employ multiple nerve cells, neurons and nerve cells, to encode things with a higher level of complexity. And if we go, the extension of that is that we think that all concepts, potentially things like even abstract concepts like algebra and bravery and political ideologies, all of these things are in some way encoded by networks, which represent subnetworks of related information. They're built of bricks, if we like, metaphorical bricks, and those metaphorical bricks are component parts of the meaning of that concept. So fascinating stuff. It means that's how we imagine we would then understand and learn anything, whether it's the difference between left and right and horizontal and vertical, all the way through to ideas such as how to calculate algebraic equations and all the rest of it. So in your own practice, obviously you're teaching students different ideas, whether it's maths, English, whatever it might be. And in those ideas, you will recognize there are some things which are very simple, i.e. they're not going to be very complicated. They're going to be relatively straightforward networks. They're going to be simple ideas that relate to only a couple of other basic pieces of information that students need to know to understand them, all the way through to very complex ideas that actually might be quite abstract and therefore are going to be requiring a lot of additional knowledge before students understand it. Like a chemical equation has lots of different components, for example. And if students don't understand all of those components, their understanding of the whole idea is going to be much more limited or inaccurate. Now, there's one other point which I've snuck in here, which doesn't necessarily relate to the rest of the basic principle of schema theory, but working memory is something which some of you might have heard of. Has anyone heard of working memory? Use the hand feature or write in the chat if you've heard of working memory. Some people, yes, about half, I think. So working memory is, oh, almost everyone now has turned around and said they do know it. So working memory is, you can put your hand down now unless you actually have a genuine question. Working memory is this idea that what are we actually processing right now? What is our brain working on, if you like? A bit like RAM in a computer. Computers store RAM, which is random access memory, which is sort of like what it's doing right now, the things it's processing right now. It can store stuff in the CPU for ages. That's like long-term memory. But working memory is what we're actually processing right now. And it's very, very limited in capacity. In humans and computers, actually. But the difference is for humans, we can't just sort of buy a bigger RAM module and plug it in. We're obviously stuck with what we have, at least for the time being, until technology gets further advanced. So we're limited to about 3 to 4 activated networks or activated schema or schemata at any one point in time. Don't worry, Verity. I'm sure we'll be able to upgrade human working memory in the future. Maybe not necessarily in my lifetime, but perhaps beyond that. So working memory in humans, it's limited to about 3 to 4 activated networks. And there are ways to sort of establish this. It used to be thought that it was about 7 plus or minus 2, but I think it's a bit more limited than that. And what this means then is you can't use many schemata at the same time. But it doesn't matter if the schema that you're trying to process is very well developed or very, very basic. It takes about the same processing power to access it and use it, which means that if you're processing 3 or 4 different schemata which you know well, so these are familiar ideas like people in your family who you know really well, or subjects that you're very proficient in and are teaching, then you can potentially be processing a large amount of information because it's all related to each other, and your brain can easily do that. It can access the network and then explore the network, if you like, very readily. But obviously bear in mind that your students whose schemata that relate to a certain topic that you might be teaching them is going to be much less well developed. They will not be able to do that. They will not be able to process all that amount of information, because for them, talking about chemical equations, for example, or talking about fractions, they might not know very much about it already. Okay, so then you've got to make sure that you're taking it. You're imagining that they're only processing 3 or 4 of their own schemata, not 3 or 4 schemata that you can access with all your knowledge of maths, chemistry, biology, English, whatever it might be. Okay. Any questions on what a schema is? At this point, I might be tempted to pick on people, but because we're short of time, perhaps we want to try and pack a lot in. And because I'm being very slightly nice to you all, I'm not going to start picking on people to explain it. But schema, rich, dense network of information encodes a concept. So let's move swiftly on to the next part. The importance of pre-existing knowledge. Okay. So we're going to start off with a task. So you're going to be shown 6 sequences of symbols. Now, I can't check that you don't cheat, but if you cheat, it just won't work very well for you and it'll work for everyone else. So I suppose you just decide if you want to cheat or not. The objective is to try and memorize the 6 sequences in 2 minutes. Yeah, don't write or draw anything. Don't make any notes. Just try to memorize the 6 sequences of symbols. They all have the same number of symbols, but they might not all be the same difficulty level, and we'll talk about that later. After 2 minutes, we're going to test you to see if you can write down the 6 sequences. Okay, so don't write anything yet. Okay, we're going to look at the 6 sequences, and then you need to just try and memorize them. I'm going to set a 2-minute timer, and then we're going to stop. So if you're all ready and paying attention, go. You memorize these 6 sequences. Okay, we're halfway. 1 minute down, 1 minute to go. They've all got 9 symbols. Thirty seconds left. Right, 5, 4, 3, 2, 1. Okay. If you've got a piece of pen or paper handy, if you've got any way of trying to write them down, try and write down those sequences. If you don't, just try and see if you can remember in your head what those sequences are and visualize yourself writing them down. Can you remember all 6 sequences? Okay. So write them down. Now, does anyone think they know all 6? Put your hand up or write in the chat. Daniela, ambitious. I'm presuming that more people would agree that they know the first sequence. Who knows the first sequence? Everyone. Really, really easy. The first sequence is really easy. Okay. Verity, what's the first sequence? If you come off mute, if you're happy to tell me.
1, 2, 3, 4, 5, 6, 7, 8, 9.
Easy. So straightforward. You got it right. Well done. Okay. Anyone know the second series? Daniela, I'm saving you to last because you say you know all of them.
Fisherman. Fisherman.
Oh, Fisherman. Yeah, there we go. Right. Third series. Marianne, try the third one.
SALOWADAK.
Perfect. Well done. Easy. Fourth series. Stephanie's hand's gone down. Stephanie, can you back yourself for the fourth one? Or not? Maybe not. Helen, the fourth series? Oh, Stephanie, no, Stephanie, go and give it a go. You've come off mute.
KJSPEQZLA.
That's for the fifth one, but it
Oh,
doesn't matter.
okay. The O2 OTTFFSEN.
How many S's?
2.
Yeah, well done. And the other one was KJSP.
EQZLA.
Well done. Now, the last series. You're missing the 7th symbol on the last one, Mary. If you could draw it and show it to me, I'll be very impressed. Now, the important thing is not actually whether you win or not, really, as I'm sure you can probably tell, but it's not a game show. But the interesting thing is, what are some sequences easier than others? Do we agree that all of the sequences, they didn't have an equal level of difficulty despite being the same number of symbols, right? Do we agree on that? Yeah, everyone agrees. So 1, 2, 3, 4, 5, 6, 7, 8, 9 is really, really straightforward. Everyone's going to remember that. You look at it for 3 seconds and you're like, yeah, I've got it. No problem. The last one, you're probably spending almost all of your time, like a minute and a half, trying to remember all these wacky sequence of symbols you never even seen. Now, I've done this before, so some of you may have seen it, but some of you gave up, which is fair enough. But this is exactly how your students feel, right? When I say how does this relate to what your students feel in your lessons. If it looks too hard, often they will just give up because they're not familiar with it. So pre-existing knowledge is really, really crucial. If you know English language, remembering a word in English is really, really easy. It's one word, one idea, you know what it is, you know what it means, and you can rapidly decode all the information about it that you need. So you can rapidly say, oh, this is how you spell it. This is what it sounds like. This is what it means. A fisherman is someone who goes out and catches fish. You get the idea. It's not a complicated idea that is alien to you. So even if you misspell it, even if you spell it wrong, you still know the idea, okay? And you understand the concept. If you know the alphabet, then sequences of letters that make any kind of, even a nonsense word, at least you can say it. So Salawadak makes sense as a sound. It doesn't make sense as a word, obviously. It doesn't mean anything, but you can say it. And this is why it's often easier to remember things in a language that's, if you speak English, as I hope most of you do, or all of you do, I should hope, then you're going to be able to see words in a related language, a European language like French or German. At least you'll be able to say them, even if you don't know what they mean. And even if your pronunciation isn't quite right for that language, it doesn't matter. Now, the next one is when we talk about just symbols that you've seen before. Symbols that you've seen before, you remember them by name. You know the letter A, and you know what the letter A looks like. You know an uppercase A from a lowercase a. And the same for every other letter of the alphabet. Same for digits, numbers. But when it comes to abstract and completely unfamiliar symbols, you're now needing to use your limited working memory capacity to actually encode details of the geometric shape of each symbol, because you don't know what they're called. You don't have a label for those particular symbols, like you have a label for every letter of the alphabet. So ultimately, we then break it down where you're like, well, this is a curly line, and this is a bit that looks like a 3, but it's got something else in it, or it's the wrong way round. There's a box with a cross in it, or whatever. These things, you have to remember it by different component parts. And this is much, much harder. There's a lot more cognitive load involved. There's a lot more effort, mental effort required to try and remember things when you don't have labels already for the individual component parts. And this is why building a schema when you don't have any related information is extremely hard. It's extremely hard. When you do have related information, it's very easy. Yeah. So if I gave you a sequence of letters and it spells the word fisherman, okay, you don't need to use any effort really to process that and to remember it and say, oh, fisherman. Yeah, that's going to stay in my head. Yeah. Whereas if I give you a completely random sequence of letters that makes no coherent sound, it's substantially harder. And if I give you completely abstract symbols in the same number of symbols in a random order, very difficult indeed. And it's all down to pre-existing knowledge. You can relate it to things you already know and then use that existing network to be able to decode information that you need. So let's look now at the third aspect of what we're going to look at. And this is about retention and strength. So what we've just covered is about learning. It's easier to learn things if you already have related information. It's very difficult to learn about Alexander the Great, for example, if you've never even heard of anything about classical Greece or ancient Greece, because nothing really makes much sense. That's its entire context. It's very difficult to learn about fractions if you don't even know how to count. Can you imagine that? Trying to learn about how to say, well, this is a half, and someone says, well, what's the number one? What's that number one? And you sort of, well, you have to go back from the beginning. So this is why we plan a curriculum in a certain way, and we have certain bits of pre-existing information we must make sure that people understand. And for your own subjects, you'll obviously be able to go away and think about, well, what is the pre-existing information that's needed for each particular lesson, or what's the pre-existing information that's needed to tackle any particular idea. And the one thing I want to go away from the second part of this session is, what pre-existing information do my students really need in order to best make use of this lesson? And if they don't have it, don't be scared to go back and change the lesson and cover it, because there's no point trying to rush ahead and teach fractions to a child that can't count, for example. Right, third part today, retention and strength of connections. So here's when we're going to get a little bit technical. Okay, has anyone heard of this phrase at the top? Neurons that fire together or wire together. Has anyone heard of this? I'm not going to ask you to say anything about it. A couple of people have heard it. What it means is this. It means if two different neurons are in some way are activated at the same time, the brain will strengthen connections between them. And in some cases, it can help to build connections, although generally it works the other way. Generally, what happens in the brain is all of the neurons build loads and loads and loads of connections with lots of other neurons, and then they gradually degrade them over time, but they keep the ones that ended up getting used. So you actually find this in developmental neurology. So with babies have lots more connections than adults, lots. Sounds a bit counterintuitive. We always think it might be the other way around, like they're going to get connections as they grow older and they build things. But actually, no. They start with loads and loads of connections. And then as they learn things, some connections are strengthened and the others are not, because some things just never happen at the same time or never get activated at the same time. And then you go through a process of gradually degrading the connections, but obviously the ones that have been strengthened don't degrade by very much. They're already very strong, and the ones that are never strengthened, that never fired together, degrade faster and eventually maybe get completely broken. And this doesn't happen at an equal rate, by the way. There's actually two processes of what's called synaptic pruning. It's just a very fancy way of saying that these connections get culled in significant numbers, and one of those synaptic pruning phases happens around age 4 or 5, and the other one probably happens in early teenage years, or maybe 11, 12. But you've got this concept that connections are strengthened, and that's what means that we can remember stuff, right? Babies remember stuff because they navigated their life and they removed a whole load of the connections that were never really applicable. They never got activated. And that's how they're learning things. Okay, so they learn that if they touch a sharp object, for example, like a pin, it hurts. Those two neurons that encode sensory pain, will fire with any information they have relating to what a pin looks like, and they'll come to associate the two. Pin, sharp and painful. And that makes a lot of sense. You want them to learn that. Obviously, as they go through in life, by the time they get to sort of their teenage years, and we're teaching them, or primary years, we're teaching them age 5, 6, 7, 10, 11, 12, whatever it might be. We're working with someone who's already got a lot of connections, perhaps connections in the wrong places if they've got misconceptions or if they've got other troubles in their life that are distracting them. But they've got all these connections, and we're strengthening the ones that we want them to remember. And we're allowing things that are not correct to be degraded and forgotten about. Okay. And the bigger the difference between the strong connections for what we think is the right answer, i.e. what we're trying to teach them, and the weaker connections for other things other ways they could go about trying to solve a problem which we don't want them to do, which are wrong. All those other ones we're allowed to degrade. And the bigger the difference, the more confident we can be they'll get a particular task right. That's the premise of schema theory and how it works in relation to retention. So rehearsal strengthens these connections. Stephanie, have you got a question or is it a legacy hand? I'm guessing because you're still on mute, it's probably a legacy hand. So rehearsal strengthening connections. So we've already talked about the idea that neurons that fire together wire together. If you've got a network of neurons that code for one concept and it always gets activated with another concept, e.g. Adolf Hitler and Nazi Germany, then you relate the two together and you come to associate them together. Okay, that helps to develop your schema for both. Obviously, you understand one concept by its connection to the other, and vice versa. There is a basis upon which this happens. It doesn't only happen by strengthening schema that activate each other. We can also strengthen networks which sometimes suppress the other. So, for example, if you know a shape is called a triangle, you know it can't also be called a square because the two are completely mutually exclusive. So you understand that sometimes there are certain concepts which suppress other ideas. They actually stop you from thinking something else could be true. Okay. And there are lots of cases where you think one thing is mutually exclusive with something else, and therefore your brain naturally will suppress those ideas. It won't give you like 100 different options for what this shape is called. It will give you the one that's the best and suppress the others. And this happens by an actual process in the brain where when those neurons are actually firing, there's chemical messages get sent back that actually ask cells to build a bigger, stronger connection, literally a bigger, fatter pipe in many ways, for those nervous messages to travel down. And that's called long-term potentiation. In case anyone really loves cognitive science and neuroscience and wants to go look it up, you can go and look up long-term potentiation and how it actually works. It's quite funny, actually. I think it actually uses laughing gas as one of its chemical messengers, nitrous oxide. So the strength of these connections is really, really important, and the more we rehearse, the stronger the connection gets. But there are a couple of other things that affect the strength of these connections, and the emotional state of people when they strengthen or when those connections are not built for the first time, but when they're strengthened, can also be really, really important. And in both directions, strong emotions can both completely suppress memory formation and put it on hyperdrive, sort of massively exaggerate it. So this is why when you have people that have experienced highly traumatic events, some aspects of those highly traumatic events will become permanently etched in their long-term memory. They'll have a very, very vivid memory of some aspects of the event. And they'll have no memory whatsoever about some other aspects which you'd ordinarily think are quite obvious. So, for example, if someone's in a major car crash, often there are certain aspects of the car crash which they remember extremely vividly. And there are other aspects of the car crash, like the color of the car they crashed into, perhaps, which you think is quite obvious, which they have no recollection of, or they think they remember, but they've got it completely wrong. They say, oh, the car was yellow and it was blue, right? So very strong emotions can really influence learning and rehearsal. And then sometimes we can use this in an educational setting to do something that's out of the ordinary of students, which arouses a lot of interest and which arouses some kind of emotional feeling, hopefully enjoyment. Enjoyment's a good one, right? They really enjoy seeing some kind of science experiment, and it creates a strong emotional feeling that they really thought it was really cool. They thought it was really fun. They enjoyed watching it. And that helps them to then understand the underlying scientific principle we're trying to teach them at the same time. Again, you might be teaching children how to count or something. And if you teach them how to count with sweets, obviously you're giving them what they think is quite a good reward. And that's, again, going to arouse quite a strong emotive response. It's an instinctive response. They want the sweets, and so if they get it right and then they get the sweets, they're obviously it's going to be more effective than just saying, oh, well done, you got it right. And so emotional factors can really influence how strong those connections are going to be. I'm sure you've all probably got ideas from your own teaching practice of things that you do to try and make students really engaged. And you can think about, well, if they're emotionally engaging those students, if those students have a feeling about what you're teaching them, that will have an effect on what they remember. Remember that it can be good, and it can also be not useful in some cases, because the more emotive they get, the more likely they are to shut out some aspects of what they're experiencing and focus on others. So if you're giving them sweets, but actually getting the sweets didn't require them actually remembering the fractions bit, then maybe you're actually doing yourself causing a problem rather than helping the situation. Because remember, the more emotive someone is when they're learning something, the more likely they are to super focus on some things and to completely ignore other aspects, because their working memory is limited anyway. And the last part of what we're talking about with in terms of retention and strength of connections is that we always go for a very normal, very natural process of forgetting. Now, if I were to ask you, is forgetting a good thing or a bad thing, what would you say? Anyone can either come off mute and tell me or put it in the chat. Is forgetting a good or a bad thing? Good thing. Both. Efficiency. That's an interesting one, Georgina. Depends. This is right. Now, when you take teachers and you don't, if I asked you at the very beginning of the session, or if I ask random teachers, I've done this before with people, and they've said, oh, yeah, forgetting's terrible. We want them to remember everything we teach them. But you've all correctly identified, actually, forgetting can be very useful. Can be a very good thing. We don't want people to remember things that are wrong. So forgetting is a completely natural process that allows us to prune out things that are irrelevant, things that are wrong, connections that are not useful. Yeah. If I say chair, I don't want you to automatically think of the Prime Minister. I mean, there's not really an important connection between the chair in my living room and the Prime Minister. There's not really an important connection between my computer and Alexander the Great. There's no real connection there. I don't want to have a really strong memory of those two things being associated. So we have to prune things out so that the schema that we have are actually useful. If I ask you to think of a house, I don't want you to think of everything possible in the world, like mugs, plug sockets, statues, political ideas, whatever it might be. I want you to just focus on things that relate to the house. Yeah. If you ask them about fractions and they're thinking about what they're going to eat for dinner, it's not going to be helpful. So we want people to forget things so that we can naturally strip away irrelevant or unuseful connections, or at least suppress them, so that you only start thinking about them if you actually activate another schema which is also relevant. So if I ask you to think about a house, obviously a plug socket is relevant, but only in the context of having electrical items that you need to plug in. If I want to know how to build a house from scratch, obviously you've got lots of other things you need to consider first, like bricks, foundations, all the rest of it. So forgetting is a completely normal process. It's natural. It's necessary. You haven't fallen for the obvious trap, which is teachers say, oh, forgetting is bad. It's not bad. Forgetting is good. We just don't want them to forget certain things. And it's in our power as tutors or teachers to practice or encourage our students to practice and think about those things. Actual cognitive engagement where they build and strengthen the connections. And once we get them to think about things, that's when we strengthen those connections. Those neurons fire together and wire together, and they don't forget. They forget the other bits that are not as relevant, and they remember the important information that we want them to know. So this leads us on to the last aspect, which is motivation and schema theory. And to some extent, there's less concrete evidence and understanding here, and some people have got questions about it. So we seem to be motivated, intrinsically motivated and interested in things where we already have existing knowledge. And also, by the same token, the flip side of that is we're not very interested in stuff if we have no pre-existing knowledge. This is why when you take students that find maths really hard, for example, and you're trying to get them through their GCSE, they don't have that much pre-existing knowledge of maths. And so any mathematical idea that's beyond something fairly basic, they really, really don't like, because they're like, well, I don't really know about it. Yeah. And then there also kicks in other factors. So, for example, they might socially say, well, I've accepted that I'm not good at this. And that's my persona. They sort of adopt this, well, that's me. I am a person not good at maths, and they then internalize that they have a low expectation of their achievement there anyway. This creates lots of motivational issues. They don't want to try because they don't think they're any good. They think that if they do try, they're not going to do very well anyway. And when they do try, because you perhaps force them or gently coerce them, they don't expect to do very well. And when they've done moderately well, they just stop, think they've done a great job. Now, in particular here, you can use this in a positive way. When people do have pre-existing knowledge about something, they obviously will be interested. So if you expose people to things, that's one way of giving them some pre-existing knowledge. They can see it, or they can experience it in some way. They've seen lots of examples of a certain word, for example. Then there'll be more things for them to be curious about. So if you show children lots and lots of plants and get them to do lots and lots of gardening, they will eventually start asking you what different bits of the plant are, or they will eventually start pointing out things that look odd, that look out of pattern. So if you show them plants and one plant has got very unusually shaped leaves, you can be sure that the child is going to notice, okay? Because they have pre-existing knowledge and they have their own internal patterns as to what these things should look like, which they're learning all the time without you needing to explicitly teach it, because they spot things. And when you've taught them this and you've just shown them lots of plants, if they see something that's out of pattern, they're going to say, oh, look, that's different, that's unusual. And it will arouse their interest. They'll ask questions. Now, the same thing will happen in academic subjects. I'm talking about plants and gardening for no particular reason. The same thing, the same mechanisms in the brain apply in any other academic subject. If you show a child, like a primary school child, fractions for the first time, say, what do you think this is? First of all, they'll say numbers, and then they'll start spotting that there's these lines in the middle. And that then can start them thinking, well, what's the line for? And then maybe that's an easy way to start teaching them about fractions, rather than just go, well, here's a fraction. By the way, this is a numerator. So we're motivated to learn things when we have pre-existing knowledge. By the same token, we're not very much motivated to learn things if we don't. If I start teaching about something which you've never even heard of, and I start going to the 5 steps ahead, it's very difficult to take people on that journey. You may have noticed in this session, I try and give lots of examples of different subjects, not just only one subject, ideally, but different subjects where I try and give examples in maths or in English or in science, where you could perhaps engage with, yeah, I've experienced having that issue with a child before. So I'm trying to do exactly the same thing. Instinctively, I try and do this nowadays. I try and give people bits of pre-existing knowledge, things they'll relate to. And I'm sure you already do this to an extent. You already relate things to topics the students enjoy or like or know about. The second point here is we're better at retaining knowledge when we ask for it. So there's a story I had here when I was teaching. A parent asked me to teach their child physics because their child didn't like physics. And they were in, I don't know, year 9 or 10 or something. They were coming up to their GCSEs. It's quite important. They passed physics, right? So I went and did these lessons with the child. And to start off with, it was quite flexible. We weren't too stringent. We weren't doing a really rigid plan. We were sort of going through bits of questions he had. We were going through a few other bits of other subjects as well. But we did do mostly physics. And I kept sprinkling in every possible opportunity quantum mechanics. Kept mentioning every possible opportunity. Oh, this is really like quantum mechanics, which is really cool. You'll learn about it one day. Anyway, 3rd or 4th lesson in, the mum comes to me quite astonished. She said, let's call him Bob. Bob's asked me what quantum mechanics is. What on earth have you done? And obviously, I've just kept telling him about quantum mechanics in a relevant context, every relevant context I could possibly find. And eventually, he thought, well, what on earth is it? So he's asked his mum what quantum mechanics is, and his mum said, please, can you tell him? I mean, it's not even on the spec, right? It's not at all on the spec. But the idea that he would just go and ask a question about physics was so alien to her, having had this experience of her son being completely against physics all this time, that she was really pleased. Now, I didn't even need to teach him quantum mechanics, but what it was good for was getting to start asking a question, because when I could then explain the answer in simple terms, he paid attention. Because people do that. When they ask a question, they tend to pay attention. So if you give people a lot of chances to to be exposed to something, eventually they'll take an interest. They'll either look up something themselves without your intervention at all, or they'll come and ask. And if they ask, it's the best possible time to teach them. And the last thing here before we go on to questions is priming. One of the best ways to try and leverage this idea of sort of using pre-existing knowledge to try and drive their own motivation is by priming. It's very similar to what I said about quantum mechanics. Keep giving them exposure to something in a relevant context so they actually understand. Now, it's not going to help if it's an irrelevant context they don't really understand. If I just kept showing him a physics textbook, which he didn't want to read, and saying, oh, look, it's this quantum mechanics in it, he was never going to be interested. Every single time I mentioned it was in a context that was a little bit interesting, like how to make your gaming computer faster. Oh, well, if we have quantum computers, then they'll be way faster, like 5 times faster. But you know about quantum mechanics another day. Now, every single time I tried to tie it to things he already knew, but they kept getting that exposure. So he kept getting that exposure linked to something he knew about and linked to something he had any level of interest in at all, whether it's his physics homework, his gaming computer, or anything else. And so priming is this tool where you just keep referring to things in a relevant context to give people exposure to ideas. It's the opposite of dumbing down, if you like. Rather than taking things away, you're adding things into the curriculum, but limited exposure. You're not teaching the whole thing. I didn't turn up to him on day one and say, oh, by the way, I'll teach you quantum mechanics. It's me to sod off in probably the most polite way. So anyway, I'm going to stop there and see if anyone's got questions. It can be about any aspect of the session today, and any aspect of if it's specific to you or if it's a bit general, then feel free to go ahead and ask. But otherwise, thanks very much for coming, and I hope you found it useful. Verity.
I have a lot of questions. Well, not a lot, but a lot of comments and questions about this.
Go for it.
One of the things, I work with children who are neurodivergent. So we're talking dyslexia, autism, blah, 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 blah. And one of the things that I have found through experience is practice doesn't always work. As much as the neurodiverse brain likes repetition, it gets to a point, it just hits a brick wall, and then the brain just forgets everything. The whole schema just kind of falls apart, which I find absolutely fascinating. And they've discovered that those with autism, they don't go through the pruning, so the synaptic
pruning phase.
Yeah, thank you. It's my dyslexia playing up now, as often as neurotypicals do, which then leads to this whole problem of, they're pulling out information. And yes, they can. I couldn't help but giggle when you said you can't link the chair to the Prime Minister. And my brain was going, yes, you can. And here you go. This is how you do it. The Prime Minister sits on a chair. That's the simplest way of linking those two up. I've completely forgotten my question.
Well, you're talking about, so about synaptic pruning. They don't go through the same process, which is true, yeah. Or there's a continuum of how people go through different processes. Some people have more, some people have less at different points.
Yeah. But I found that really, really interesting. So thank you.
No, you're very welcome. And you're absolutely right. All of these things can be linked. If you challenge someone to link it, or they're motivated to try and find links between it, they can. It's just, if you go into an exam and you get a fractions question, you maybe don't want them to start going, oh, let me write a story. It's totally fine if that's what they would instinctively do. But obviously, when we're trying to get them to be able to respond to certain tasks where there is a right answer or there is a desirable kind of answer, obviously, in a teaching context, generally we have some kind of desirable response. We want them to write a well-crafted story that's interesting, or we want them to be able to calculate how to solve a problem, or whatever it might be, or we want them to learn factual information. Sometimes it's just they need to know times tables. then yeah, absolutely, it's relevant that there are some things where we want them to focus on and some things we don't want them to focus on, despite the fact they can. And you're absolutely right. The neurodivergent bit is really, really interesting here, because there is an almost perfectly smooth continuum of how much synaptic pruning happens at what stage. And there is obviously a very normal kind of most synaptic pruning happening around a certain time, and you could try and measure how much synaptic pruning is going on, although I don't know of any studies that have effectively managed to do that. It's quite hard. But you can have typical synaptic pruning, which is sort of very much close to the average, and you can have atypical synaptic pruning, where either it's more aggressive, less aggressive, more connections are culled or fewer, or that it happens over a longer time frame or a shorter time frame. And inevitably, this gives rise to very significant differences. And children that end up getting, I don't like using the phrase labeled, but if they're labeled as neurodivergent in some way, then you've got to study. Yeah, I was going to say, if they're labeled as neurodivergent in some way, it's probably to do with a developmental neurology not taking the completely average track. In the other cases, it can be in some cases due to some combination of external environmental stimulus. So sometimes there's something which causes things to happen. Oh, this is fantastic. There we go. Thank you very much, Verity. I'll have a look at that. But in some cases, it's environmental. I mean, people can obviously suffer brain damage or be exposed to chemicals which cause things to happen in their brain. But in many cases, obviously, this is just completely natural. In terms of the process that happens, can just be very different for people. And that can happen to a greater or lesser extent. It's not necessarily it's different or right or normal. It can be mostly normal, but not quite as much. And the continuum is a continuum, not an on and off. Daniela, did you have a question?
Yes. I discovered the cat's brain in my maths lesson. For example, students that are not able to represent graphically a 3D solid. And this is typical. And yeah, I manage with some other physical methods. But I wanted to ask you how, when it is about evaluation, for example, I have students in my class that are brilliant in the lessons, and they are not able to translate in the tests whatever they learned, and they are falling so easily in doing mistakes. Do you have a method for this?
Okay, in my experience, tests do two things. First of all, there's stress and anxiety around the result, right? As soon as you stress somebody, okay, they start using some of their cognitive capacity, worrying about the outcome, which obviously is cognitive capacity, which, given they've got a finite working memory, they're not using that cognitive capacity to process the actual question and try and work out a solution.
That's right.
Now, the second thing that causes a problem is time pressure. And I'm not sure if it's exactly the same process or if it's just a related process, but you can try this very easily, right? I actually did this in front of the parents of a boy who was in year 5. This was many years ago. He's not in year 5 anymore. I think he's actually finished his degree now, but he was in year 5 and his parents had called me and said, look, he really, really struggles. Exactly the same case that you're talking about. He really, really struggles on his maths tests. He's really good at maths, but when we sit him down and ask him if he can do the processes, he can do it. But when he goes into his tests, he gets a really bad score. What's going on? So I showed them. I said, look, watch this. I'm going to give him a test with no time limit. 20 questions. All questions that you should be able to answer. And I'm going to give him another completely comparative test with exactly the same kinds of questions, but I'm going to time him. I'm not even going to tell him he's only got a certain amount of time to do it. I'm just going to say, I'm going to time you. And the difference was enormous. He got like 18 out of 20 for the first one. And I can't remember what it was now, but it was something like 12 or 13 for the second one, where I hadn't even said to him, you've got to do it in 5 minutes. I just said to him, I will time you and write down what time you get. Yeah. And the difference was very significant because as soon as I said I was timing him, he was rushing. He wanted to do it in a faster time. So one of the best pieces of advice I have is to always encourage students to first of all focus on just getting the questions right. Doesn't matter how long it takes. First of all, get the questions right, and then only focus on getting faster when they can reliably get it right every time. Yeah.
Yeah.
Interestingly, this was exactly the same way I was taught to play piano, and I'm not very good at piano now. I'm not a pianist at all. But when I was taught to play piano, my piano teacher, I remember this bit quite vividly. He said, just go really slowly as you like. Doesn't matter how fast the piece is supposed to be played. Just go really, really slowly, but make sure you press the right notes. Once you can press all the right notes in the right order, then get gradually a little bit faster until you're playing at the appropriate speed. And I think that's actually really good advice. I mean, obviously, I wasn't a teacher at the time. I was a student. But looking back on it, that was fantastic advice, because what's most difficult is actually being able to follow through the whole process to answer the question correctly.
Yeah.
Once you can do that, just keep practicing that until it becomes second nature and really easy and routine. But don't worry about timings until you've got that really reliably done. And once you are once it's really second nature to you, or once it's really quite easy, speed comes as a byproduct. You don't even need to focus on it. If I keep asking you to do, I don't know, to come up with definitions in biology, for example, eventually it'll just be so easy for you that you'll do it really fast.
Yeah, that's right. I will try this.
Good luck.
Try this. Thank you.
Any other questions? Marianne.
Hi, it's just a comment really to build on what Verity was saying about neurodivergence. It's just to bear in mind that I work with a similar type of client as Verity, and obviously with neurodivergent clients, I'm thinking about sensory considerations all the time, and it's very, very powerful. And I found with my non-neurodivergent clients that sensory considerations are equally important. I think we just think about sound and light and texture and all that with our autistic students, and to a great extent dyslexic students as well. But actually, I find it with all students. The more I've learned about it through my neurodivergent students, the more I'm learning about it with my non-neurodivergent, that sensory, the environment, textures, internal hunger, thirst, all those very basic sensory needs are incredibly powerful for learning. It's so basic that we sometimes overlook it. And it was just a comment really that I can hear what Verity was saying about that. Things seem to fall out, it sort of falls out of their head. And I find if you make your students very comfortable sensorily, think about that, and looking for those little cues. I have a sort of little group of girls that smile a lot when they absolutely do not know what I'm talking about.
Yes.
And just knowing that about them, knowing those little cues, really helpful to know. So yeah.
No, definitely a really interesting comment. And actually, we didn't have time to really go through the connections to this in a lot of detail, but this emotional part, which I've brought up here, which I can sort of highlight on the screen, and this part about emotions affecting emotions, when you rehearse anything or when you even learn anything, the emotions play a big role, and that can be an emotional response can be created simply by someone being particularly comfortable or uncomfortable. So someone desperately needing the toilet, for example, they're not going to possibly learn anything very effectively, apart from I really need to go to the loo and this person's horrible for not letting me. And I appreciate in schools, obviously, there are practical considerations of children getting up and going to the toilet left, right, and centre all the time, and some children abuse it if they're allowed to. But obviously, in a tutorial setting, just let them go to the toilet anytime if they need to, or if they're not comfortable, let them sort that out, because otherwise it will distract them much more than it's worth. And also, if some children are more or less affected by this, but everyone is affected by how comfortable they are, and if they're wrapped in a soft fluffy blanket and that makes them really happy, and they can really focus and enjoy something when they're doing that, that's not necessarily a bad thing. I mean, it might look weird that they're wrapped up in a blanket, but if they actually learn really well doing that, it's not necessarily a problem. Who am I to say they shouldn't? I mean, I don't care if they're wrapped in a blanket when they learn things, as long as the sensory stimulus can't then distract them from what they're doing. Otherwise, what you're doing won't make any impact. But absolutely, really, really valid that they're how they feel and the emotional processing they have, which is all done in the brainstem, which is much more pre-conscious or subconscious process, does have a massive impact on how effectively their brain works at the very top level, if you like, for cognition. And if they're struggling to breathe in an extreme case, for example, they won't process anything else apart from I need to be able to breathe, right? And likewise for comfort and discomfort in any form, or pain in any form, that's going to massively impact their ability to learn anything. On that note, we're going to wrap up for today. Thank you very much to everyone for attending. We will publish the recording online, but really, it's really good to see you all, and hopefully you found it useful and interesting. If you are interested in attending the next of this mini series, it's on Wednesday the 24th of July at 1 p.m, where we're going through cognitive load theory. Okay, thanks so much, everybody.